Okay, in this exercise, we have an exercise bicycle, or just even a regular bicycle, and we're pedaling it, and we want to know how quickly we need to pedal, how quickly this needs to go around here, so like a rotational speed, in order for this bike to rotate at 75 RPMs, right? So this omega is equal to 75 RPMs. And we want to know how quickly we need to spin here. So this is the question. Um, so the first thing that we need to do, that we need to note in order to solve this, is we note that, well, this little 3-inch wheel right here, this 3-inch diameter, is connected rigidly with this wheel here, and so they both have the same rotational speed. This one, when this makes one revolution here, this one makes one revolution here as well. Okay, so that's the first thing we need to note in order to be able to solve this. And so we can say here, let's just say I'll give the like a subscript for the diameters here. Let's say the omega of this 3-inch wheel is the same as the omega of the 24-inch wheel. Okay, and we want to find the omega of the 8-inch wheel. This is what we're looking for. Okay, now the way that they're related, we have this system here with this one spinning around and this one spinning around, and the relationship we have between them is this bike chain, right, or this rope, or whatever it is, most likely a chain. And so we have this chain right here, and the thing that is the same throughout this chain, regardless of where it is going to be its speed. Not its rotational speed, obviously, but its linear speed. And so we can say that if there's a linear speed right here, right? Some v. Actually, let me make that more over here even. There's a linear speed right here. This is v. And this is a linear speed when it's like next to the 3-inch wheel. And then there's some linear speed when it's next to the 8-inch wheel as well, right? And because this chain, has to be moving, the whole chain has to be going at the same speed, right? I can't have different speeds. This one over here, I can't be moving at like 2 meters per second, and then here 1 meter per second. And then I would have, the chain would be getting backed up over here. This is later on. This is something that we'll build on. We'll call it the equation of continuity. We have to have the same speed, the same amount of chain flowing past the same point at all times. And so, so we have to have these are the same. So we have here V8 is equal to V3. But remember the linear speed, the tangential speed, is equal to the radius times the angular speed, right? So that's the radius of this 8-inch times the angular speed of the 8-inch. And V3 would be the radius of the 3-inch times the angular speed of the 3-inch, right? And so I can take this equation over here, and I can say that R8 omega 8 is equal to R3 omega 3, right? And so I can get this relationship pretty easily for the angular speed of the 8-inch wheel. I can say then the angular speed of the 8-inch wheel, omega 8, is going to be the radius of the 3-inch divided by the radius of the 8-inch times the angular speed of the 3-inch, right? And actually, since I am just getting a ratio of their radii, then that would be the same as the ratio of their diameters, right? And so I could say here the angular speed of the 8-inch would be the diameter of the 3-inch divided by the diameter of the 8-inch times the angular speed of the 3-inch, right? So it's just a ratio. The speed at which I have to pedal this one is this ratio times the speed at which this one turns, right? So if I want this to turn at a speed of 1, then, well, I need to know the ratios here, but it's just a ratio. So I have a ratio of their speeds, or a ratio of how quickly I need to spin them, as a ratio of their diameters, right? Actually, we call this the gear ratio. The ratio between the, maybe if I write it out actually a little bit differently, omega 8 over omega 3 is equal to R3 over R8. So the ratio of their angular speeds here is equal to the ratio of their diameters, or their radii. But these are flipped, an inverse relationship. So yeah, the bigger one has to spin slower, right? So anyways, we can use this to solve this problem. We note that the rotational velocity of the 3-inch was the same as the rotational velocity of the 24-inch, which was equal to 75 RPMs. That was the whole thing. How fast do we have to spin the 8-inch to get the 24-inch to spin at 75 RPMs? And we know the diameters, right? Obviously, the diameter of the 3-inch, and the units are trivial here because we have, as long as they're the same, like meters and meters, inches and inches, feet and feet, etc., because the units will cancel out. And so we have here omega 8 is going to be equal to 3 inches divided by 8 inches times 75 RPMs. And I don't even need to bother converting to like radians per second or anything, because I'm just looking for the speed, and it's just a ratio, right? And so omega 8 is equal to 28 RPMs. So I need to pedal at 28 revolutions per minute in order to get the back wheel up to spin at 75 revolutions per minute. And when you go to higher gear ratios, right? If you have a mountain bike or something like that, then you have smaller and smaller diameters here. The smallest diameter here is actually your highest gear ratio, right? Smallest here and biggest up here give you the biggest gear ratio. So you pedal this one, the faster you pedal this, it magnifies this one more and more, which is what we see in this relationship here, or